righty. So we have a ton of content to go in here. We have a little space at the end. We might try to stick some demos in, but this thing is just packed. So I wore my stretchy pants, and I hope you all did, because we've got a Elixir by the Bellyful here. There's me on Twitter, hashtag, and any questions you have, just throw them on Twitter. I'll get back to you as soon as I can. The code from this is going to be on GitHub, and we are off. Okay? So as you come to Elixir, all sorts of questions. You come to any language, all sorts of questions. There are all these things. You look around and you say, okay, what do I know that I don't know? And what do I not even know that I don't know? And so as we look around, we're looking for sea monsters. We're looking for the pitfalls, the traps, the places you can get hurt. And you're also wondering about the fun that's out there that maybe you don't know about yet. And so the good news is in Elixir, there's a whole lot more fun than there are sea monsters. And so that's the good news right now. But there are quite a few things that maybe you're not familiar with yet, and we're going to try to hit as many of these as we can in 40 minutes, which is kind of insane. But so we're going to talk about this chain of bits here. Is there something on here that you don't know? All right, see some hands, see a bunch of hands. Okay, here we go. So let's start off with a bit of history. So the beginning of Elixir was when Jose, he's a core member of the Rails team, Ruby on Rails, and he's facing these problems around concurrency. He's facing these scalability problems. Of course, lots of people are facing those kinds of problems on other stacks. You know, he was in an interesting position, though, being this core member. And so he's a curious guy. He's out there looking, and he sees Bruce Tate's 7 Languages in 7 Weeks book. And it sort of lit him on fire because of this chapter in there on Erlang. So it's interesting. So when he found these solutions to concurrency and scalability there on the Erlang side, why didn't he just become an Erlang developer? Well, maybe if you looked at the syntax or so on, you would understand maybe why he didn't become an Erlang developer, but it wasn't about the syntax so much. And if you saw the tool chain, though, that might be it. But then the other question is why didn't he just steal Erlang bits and bring back to Ruby? And so we're going to find out a bit more about that. And we're going to find out why in 2012 he went on this wild, crazy journey and Elixir hit V1 and brought the community along with him rather than him leaving the community. So why Erlang? So Erlang, the story begins at Ericsson. This is in Sweden, Stockholm, the giant telecom giant. And they had problems back in the 80s that most companies didn't have, but lots of companies have now. They had to deal with lots and lots of concurrent users, and they needed to have availability. So they couldn't fall down. If they fell down, that was disaster. So they had this lab here. We have Joe Armstrong here, and Robert Verding, and then Mike Williams here. And they were in this lab, and their whole job was to find and solve problems that were in problems of telecom then. So the problem, again, high availability. So you can spend a lot of money, and you can get really good equipment, and that can help you on high availability. But then things can actually even go wrong on good hardware. Things can go weird in the environment, and things can go weird in your code. You can have faults. So to have high availability, you have to be fault tolerant. And this is the #1 goal of what they were doing in their research there. This is what they were trying to solve, fault tolerance. So you have 100,000 phone calls, something goes weird, and you're running your 100,000 calls, and you have some sort of crash, and you crash your process, and 100,000 phone calls die. Well, that's terrible. That's definitely not high availability, and so that's a total disaster for them. So they needed to be able to say, okay, how can we have things fail independently? And even better, like how could we have a reasonable sort of view of the world where we're handling each one of these things independently and they crash independently? So then they started digging into concurrency. So with concurrency, they could fail independently, they could run independently, they could code these things as sequential blocks of code that were easy to reason about instead of these crazy thread monstrosities that the rest of Ericsson was building and the rest of the world was building that had this kind of problem. And so that gets you a long way. But then what happens, you've got your 100,000 processes running on your computer here, and that server falls down. Well, you have to also solve the problem of distribution. You're not fault tolerant if the server goes down and you're fully down. That's not good. So these are the things they were focused on. And together, through their work, the first product that shipped with Erlang, and it was the AXD301 switch, it went out into the world, and the first product, it replaced this C++ monstrosity that never quite made it. It went out, and British Telecom, the first project, it hit 9 nines of uptime. So this is 30 milliseconds a year, something like that. This incredible reliability on its maiden voyage out, which is just amazing. So why did it happen? How did it happen? It really came down, it was around the Erlang VM is a big part of why it happened. So what in the world is that? So the Erlang VM doesn't look like a normal stack here. So we've got this OS, Windows, Linux, Mac, and so on. We have this Erlang VM or this Erlang runtime system here, and it's way down into the territory of that box where you'd normally be up on top of these operating systems. So the Erlang VM is an operating system. It's not a peer of the JVM. It's not a peer of the CLR, the .NET CLR. It is an operating system. It can run on top of other operating systems like Windows, Linux, Mac, and so on. It can run different hardware architectures, Raspberry Pi. You've probably seen the nerves content, just stunning stuff there. But up on top of that operating system, we have a set of libraries that were built at Ericsson called OTP, Open Telecom Platform. And so these were these libraries that they had built all the way from '86 on to now, just making more and more stable of how you build these core bits of software, all the lessons learned, battle-tested lessons, and there are these reusable patterns that are cooked in there. There are these libraries and then just general patterns as well. That makes up OTP. On top, we have these languages, and these languages on top, they compile to the Beam. So Beam, B-E-A-M, is the byte code that you compile down to from Erlang and from Elixir. So Erlang, Elixir, absolutely the same as far as the Erlang VM is concerned. And this is our first reason of why Jose didn't just say, I'm going to take the good ideas from Erlang and bring back to Ruby, because there were hundreds of developer years put into the Erlang VM. So that's a lot of work to bring back, and it had this track record. It was doing all these amazing things. And so instead of doing that, you come over to this thing. Now, I want you to see this none over here. This is interesting. I'm just going to point out a couple of examples. So here's one, Erlang on Zen. If you do a search for this, it's a pretty cool project. This is bare metal hypervisor. It runs on the bare metal on the Zen hypervisor, which Amazon EC2 uses. And so you can spin up boxes there. There's a demo here that will bring up an instance of Erlang on Zen and service your web request, send the response back. The server gets destroyed, goes away, and that all happens in the, let's see, the 0.3 seconds there. So booting into a server, web server, response comes back, 0.3 seconds. We also have there are several projects along this line, but Grisp is bare metal on this embedded device. So this is one to search about. Very cool stuff, but it's outside of the scope of what we're talking about here. So we now have to think about, we know Erlang VM is an operating system. So what is it that an operating system is even responsible for? And so it's about process management, interrupt scheduling, memory management, file system stuff, networking, all these bits. And this is, Erlang VM takes on this. It doesn't count on, there's like, for example, there's no even concept of threads inside of the Erlang VM. So all these operating system concepts, they don't bubble up. It's a different abstraction. So what is it that an app does? So if you write your C code, your C#, your JavaScript, well, it has a different job. Its job is to go out there and eat brains, because its full-time job is to try to get as much core as it can. It's trying to perform as fast as it can. It's trying to get its job done, and it doesn't care anything about the job of the operating system. And the operating system, as a result, is in this battle with it. This is like this zombie warfare going on between the operating system and these processes. It can't trust anything. Everything's bitey out there. It's trying to get its hands on you. And so the operating system has to lock down memory, these costly, painful context switches between things as you switch back and forth. No trust, no trust, no trust. So it can be different than that, though. And it is different than that on the Erlang VM. Here, the Erlang VM isn't a general-purpose operating system. It's a special-purpose operating system, and its special purpose is to make sure that Beam code has a rock-solid place to go off and be awesome. And so that is us. We're writing our Beam code, we're writing our Elixir code, and this VM, its full-time job is to make sure that we get everything that we need, and it knows it can trust us because it's not that it knows we're good people, of course we are, but it knows that that's not why. It knows that we can't break the rules. They agreed on the rules. And so now we're going to see a little bit about this model in action. So here we have the shell, interactive Elixir. So IEX, we come in and we type in self. We see a process ID. So even the shell itself is a process. Everything's a process. It's processes all the way down in Elixir. Okay, let's talk just a bit about concurrency, because this is one that's easy for people to mix up between concurrency and parallelism. They're not the same thing. So concurrency is about the structure of lots of things at once. And parallelism is about the execution of lots of things at once. And so if it were about parallelization, it would have never happened at Ericsson. You would have had, back in '86, they didn't have multi-core boxes that they were running Erlang on then. What they needed, though, is they needed to be able to reason about lots of things at once, and it just turns out that model works really, really well. And so in 2006, they were able to flip the switch, go to multi-core, have multi-schedulers, and processes code that had been written 10 years before, deployed to new Erlang in 2006. 2 cores ran twice as fast, 4 cores ran 4 times as fast, and there were cases of good Erlang code that would shown to scale linearly up to 40 cores, which is crazy awesome. It's a total moonshot that happened there. So let's look about these processes. Let's learn a little bit more. So every actor, every process, has some props. So the first of these props is memory. So each of these processes, they have their own dedicated, isolated, share-nothing memory. And it's tiny. It starts off tiny anyway. It's a kilobyte, 32-bit system, a couple kilobytes on a 64-bit system. And inside of that, we have this heap in the stack. And as we build up, our processes are running, and they accumulate state and so on. It grows, and it grows following this Fibonacci series. So it can grow and grow. And after it grows, though, it can be garbage collected. Okay, each process gets its own garbage collector. So let that sink in for a second. We've got hundreds of thousands of processes running on a box, and each one of them has their own isolated garbage collector. So you think about this job of garbage collector on a VM where it's functional, you can't mutate state, and you have no shared state between processes. It's not a bad place to be a garbage collector. And we get something out of this. This wasn't just to be awesome and cool. There's plenty of things that happen there. This was around, again, high availability fault tolerance. When you have these tiny deterministic GCs that happen, you don't have a stop the world GC that brings your whole server down when things get busy and you're putting off a GC, and then it's, I gotta have a GC. And so that kills availability on some systems. JVM, CLR, you'll see that happen. All right, every process gets its own dedicated mailbox. And it's a good thing because this is the only way a process can talk to the outside world. It's absolutely lonely being an Erlang process. You have this message box, this mailbox, and you can send things out of the mailbox to another process, and you can receive things back in your mailbox. And you can choose when to send and when to receive. Things can accumulate in your mailbox. You don't have to just accept it then. It's up to you whenever you fall into your receive block. Now, this is real here. So, like, it's not just sometimes you talk through the mailbox when you need to do something and talk to the outside world. It's every time, including file I/O, talking to the network. This is all message passing. So if you've done file I/O, you probably said file read, file write, something like that. What you're doing in the background, though, you're talking to a process, and back in the back, it's doing gen server talk. It's talking back to a port driver. So anytime we're dealing, not with just another process, but anytime we're dealing with the outside world, we're dealing with side effects, we're going through a port driver. And so in a funny way, as you run across Erlang and you see this ecosystem, there are all these functional concepts, but they're not the same as you'd see in other stacks, like the idea of like a monad, the I/O monad to protect you from side effects and so on. It's hidden underneath this layer, port drivers, and that's where all the isolation is, but we have these guarantees inside of the mailbox of message passing, this copy-only message passing, which is pretty darn cool. Okay, so, and then the last thing that we're going to talk about as far as processes is what they come with is links and monitors. And so when we're talking about the process being able to, like that phone call crashes and you're able to bring that phone call back, maybe even before the caller even notices anything happened, anything weird happened, you do this through links and monitors. So a link is like a death pact. It's like this process, if that process dies, I'm going to die too. And if I die, it's going to die. You have this death pact with the other process. We have to work together or we can't work at all. And this other idea is monitors. And that's where I want to know if you die. I'm reading the obituaries rather than actually signing up on the death pact. It's like, I want to know, I care about you, but I'm not willing to go out with you. Okay, so now let's look at how this all orchestrates when we have more than one of these things. So process scheduling. We have a single CPU core, we get a single scheduler. So we have 3 processes running up on this Erlang VM. We got our Elixir processes running, 1, 2, 3. And we have this game here called reductions. So each process, the scheduler gives 2,000 swipes at the core, and there's a almost zero context switching cost as you go from process 1 to 2. So we see chunk, 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 and then it repeats back to process 1. Now there's nothing that process 1 can do to hog the core and hold it. This is preemptive scheduling here. So it takes the talking stick away after 2,000, even if it's in the middle of calculating pi. It doesn't matter if it's trying to be a hog or not. It just removes it. Everyone gets the even swipe. Here's another visualization of that same thing. And if we get multiple cores, we get 2 schedulers, 1 per core, and they're chunking along in parallel then, and so on. And you won't believe this is actually a PowerPoint animation. So that's yeah. So, all right, so let's look at supervision and this idea of letting it crash. So here we have 2 processes, a supervisor and a worker. And if the worker is going along and it is chunking, and it's talking to the network and something weird goes on the network, there's some sort of blip, it crashes, supervisor restarts it, and the worker returns to its last, to a known good state, where it was at when it was spawned or so on. Okay, now let's look at 3 processes here. We got one chunking along, and it says, hey, I'm going to wait and look in my mailbox and see if there's anything there. I'm going to fall into a receive block. I don't really have anything to do until I see something there. Okay, it falls into this receive block, and it's going to block forever. It's going to block, and no one's sending it messages, so it's going to block. Have we just wrecked the whole show? Have we got a single threaded event loop where we're blocking and the whole show falls down and we've got that mess? That's not what we have at all here. We have this, what happens here, when this guy blocks, it's not a bad thing, it's actually a really good thing, because then what happens is the scheduler rotates that process out of the loop, and the Erlang VM doesn't bother bringing it back into the loop until it knows that it has a message in its mailbox. So that's pretty cool. And then our next process carries on. Okay? So now let's talk about migration. So we have all these processes, we have all these cores. How do these get there, and how does this work? And it's a game of balancing and compaction, really. So we want to compact for energy savings and for memory locality. So busy, I'm not so busy. I can pull something back over, and it comes in, and we've got more to do here. And this core can just go to sleep then. The other side of it, we've got a little too much building up here. We have work stealing, and it moves on over. And these are all things that are happening for us automatically. Without us thinking about it, this is just the Erlang VM handling these things for us. But now you have a little bit more of a foundation of understanding how all this stuff works, and it's powerful. You don't end up in the guts of this so often, but it's nice to know that it's there and how it works. And so with this, we have massive concurrency. We have preemptive multitasking, concept of soft real time, so that this guy isn't going to cause the latency to climb for other things, and you have this even deterministic scheduling. It's a sane place to write code, run code, maintain code, and be ops. It's also really, really fast. So, and it's fast because at the very beginning, when Mike Williams was there with Robert Verding and Joe, they had this idea of, well, Mike talked about this. He said, the performance of a concurrent language is predicated on 3 things: the context switching time, the message passing time, and the time to create a process. So you're really fast at those things, you're going to be really fast. So let's look at just a bit of Elixir code here. So we have here this loop, and its whole job is to test Mike Williams' idea. So our job here is we're going to spawn a process. So we call it into live a full life. We're going to spawn a child process, and it's going to be one less than us. So if we kick this whole chain off with, say, 100 processes, we want to see how long it takes to create them, have message passing, and so on. So we say to live a full life, so 99 you, the next one's going to be 98, and so on. We're going to count down to 0. So we create a child, and we send that child an OK message, and then we fall into receive block, wait forever and ever and ever until we receive an OK message, which will come from our parent, right? Just as the logic of it. And so this chain right here is testing all those things, spawning processes, sending messages. You have context switching because the scheduler's having to go from this one to this one to this one, and this one's waiting in a receive block forever until it hits and it catches. So when we run this, on my laptop here, I run 1 million of these, and it runs in 1.1 second, almost 1.2, but that is insanely fast. And so it's good to have that number in your head whenever you're thinking like, do I hold off? Do I not create processes? Well, you can probably create processes. You can probably send messages because it's super, super cheap. And you hear it's cheap. You see a number like this, though, and you realize, okay, I don't have to worry. Okay, let's talk a bit about the language. Oh, let's talk a bit, not about the language, let's talk a little bit about OTP. I saw the wrong bottle. So, safety and fault tolerance. So we begin with gen servers. So gen server, you're going to use a whole lot in your Elixir applications. This is the go-to sort of generic server. It's a general purpose server. You live on top of it, you write your custom logic, and you get all the benefit of what Ericsson did over all those decades. And so here's a tiny bit of code, like a tiny little gen server, that shows us basically how we would basically have a counter we're going to bump up. So we have this chunko worker, and it has a start where we're going to kick the thing off, and it has a bump level where the callers are going to bump our level up, and then back in the back we have this init and handle call. Well, that's maybe a little hard to grok if you haven't seen this before. So let's look at this in a different way. So we're going to frame this here instead, so that we see over here we have a caller, we have a client API, we have a callback, and a behavior. And so the behavior, in this case, was written by Mike and Joe and Robert, the gen server back there, and then this gen, and then by the Elixir team inside of the gen server that sits on top of those. Okay? And our chunko worker, we wrote, and it has a client API and a callback, and then the caller is just going to be the shell in our case here. Okay? We see, too, that we have this separate concept over here of modules where the code is, and a process, because these are really different concepts. Like one process can run code from 1,000 different modules, and one module you can have millions of processes spun up running that code. So those are separate concerns, separate ideas, and so that's just one to kind of click here. So in our IEX, we start, and we come in, and so we've called, inside of our client API, we've called the start function. And the start function inside of chunko worker, if you notice, the start was running in the same process space as IEX. But then when we call from start down into gen server start link, we've started a brand new process with a different process ID, and that code is running down there. So start link, the first thing it's going to do is it's going to go back into our callback. It's going to call back into the callback and call its init. Inside of our init, we set our initial state, pass that back to our gen server, and then we return back with our process ID. And so that's one way of visualizing the life cycle. So it's kind of good to have a few different views, different perspective on how this works. So back to the code. If we move this over and kind of zoom in a bit, we see we have our bump level up at the top. So we're in a server loop now. Our gen server is forever and ever running in this tail recursive loop. It's starting, it's waiting for messages and so on, and our gen server is going to run forever. Our bump level up here off in our caller space is there. And so our loop is going to wait in our receive block, and when someone calls into then bump level and does a gen server call back to us, we're going to get that message. Our gen server is going to get that message, and it's going to dispatch that message over to our callback, the handle call, which has the shape that matches our bump amount value. It's going to run that code, and at the tail end of that, we're going to do some logic in there, our awesome business logic in here, a response and all this. And then our reply is going to have reply, and it's going to say whatever response is and what our new state is on the tail of this thing. That's going to come back in, and we're going to send our reply back up to our caller, and then the gen server updates its state, and then it returns back in that loop. And so that's what's happening for you on the back inside of a gen server. That's all the code you're not having to write. There's all sorts of other stuff in here around hot code loading as well, but this is a simple view of it, and hopefully this cleared that mystery machine up that is gen server. So in OTP we have applications, and so applications is basically what's going to spin up all of our stuff. So we have our Chunko worker. We've mixed nude Chunko worker. We have that thing running. When we start our application, it's going to come up, and a lot of times we structure these so that our top level, at the top level, we have a top level supervisor. This top level supervisor is going to make sure that if anything dies, that it gets restarted. Say like we have some gen server over doing work for us. And if that gen server dies, this top level supervisor will bring it back. Supervisors can also supervise other supervisors. So maybe we have a supervisor over here that has some special rules around how it's going to restart its gen server. And maybe if they go wild and one of them crashes, it'll actually could cause that supervisor itself to crash, and we need to restart that supervisor by the top level supervisor. And so this is called a supervision tree, and this is how you end up with these systems that run and run forever without falling down. So you run and run forever without falling down because you let it crash, which seems like a strange phrase, but this is a mantra that works well in the Erlang community, worked terribly with the business community, and it's probably why the first time we see this major adoption is on Elixir, where we prefer to use the phrase code the happy path instead of letting it crash. So really, we're not worried about our edge cases is what it comes down to. We're focused on when things go weird, just let it crash, and a supervisor brings it back into life. Our code becomes much simpler. We don't have tons and tons of edge casey code. Okay? When we're trying to code massive concurrency and we need it to work, the easiest code in the world to write is sequential code, just top to bottom. And that's what we write in Elixir. Our Elixir code is just sequential code. We're not dealing with threading or any of this rocket surgery. Everything's bricked and so on there. So another idea that's developed out of this community is no masters. So instead of having, there was a thing called the Microsoft DNA architecture, which had this idea of some service runs here, it has this role, and it's going to call back to this other layer here that's going to have this role, and it's going to call back through. So you had all these different layers with different responsibilities. And so you had these things working in series. And basically, if any one of those layers failed, your whole app was down. So you had 3 reasons to fail. If anything failed, you were fully down. So the idea of no masters is really about having a series of peers, where every box has the same capability. And if one goes down, another can just take over. So here's a way of looking at this statistically. So if we have in series, we have 2 systems, 2 components that have 3 nines of reliability. We put them in series, we end up with 17.5 hours per year downtime. And if we put them side by side, where they're not, we can go to either route, we end up with 31 seconds per year of downtime. That's quite a different outcome. Okay, now we're at language. So the language is accessible. It starts off, we can even go to Elixir Lang, and we actually have a useful website where we can learn about this language. There's lots of stuff here, including a 1 to 22 list that will take you from not knowing anything to knowing how to be an Elixir programmer. And so if you know of people you're trying to get them to ramp up, this is really the best place. They can really follow this site. People just assume you can't go to the language website and learn anything because they're all so bad. But this community is so good that language website is good. And then the community is growing. We've got 300 or 200 and something meetups, and it's all over. And it's warm, not just at the local level, but even on the core team level. So you find some neat addition, you send in a pull request, and the creator of the language sends you a merged with an exclamation point and multicolored hearts. And so that's really amazing. We've got this incredible steward of the language here, and we're so lucky. Hex is awesome. Hex, the package manager, it basically takes every good idea from every other package management system and then removes all the bad ideas that were there. We have these immutable packages, unlike some other platforms that creates trouble. And we go to a particular package in here, and we just see the level that these are at. I mean, the docs are good. We see these bills pass. It's just amazing how good this community is. And it's built because the tooling is expressive and good and modern. It's easy to create a hex package. It's easy to consume a hex package. It's easy to create the docs. It's easy to do all these things that we want to have happen. We're not having to fight our tooling all the time in Elixir. So let's talk about modern tooling. Our modern tooling is, really, we go back to the REPL. We go back to the console. And it's a funny sort of retro idea, but this is the best of modern tooling here. We go and say H&M. We tab through, and we see all the things that are under the new module, which is really amazing. You know, that's so cool. You can build your code up through here. You can explore here. And inline, we get our help. We see what it's for, and we see an example of the usage. That example of the usage here, all it took for them to do that was here. You put in the code inside of Elixir, we see @doc, and we have our string. And this thing here, though, this is not actually just documentation. It's not just, it is nice documentation, but that's not all it is. It's also a doc test. So if I decide, oh, I'm going to make count even better, I'm going to return OK and then the count or something, and I change count, and I send them a pull request in, well, what's going to happen is that is going to break this. This is a unit test. So when you build Elixir and you run your unit test, all of the doc tests run as well. And if this is no longer true, that build fails and that version of Elixir never makes it out into the world, which is really cool. Mix. So this basically replaced this miserable 2 decades of IDEs. So we have here mix, and we have all these tasks that we can do. We can scaffold out new projects, we can compile, we can generate docs, we can run tests, and so on. So we scaffold out new FizzBuzz, and bam, we've got a full-on project with tests that we can run, and it's good. Expressive dev joy. Let's look at some of the bits in the language here around matching and why this is such a productive place to be. So we're going to kind of blaze through some of these bits, but we have here a tuple on the left. We're matching against our apple, banana, cherry. And we go through, and our B is now bound to banana. So we get this destructuring happening. A list, 1, 2, 3, case. And so we're going to put up a case expression here, and we're going to pattern match against our list. The first clause in our case, is this going to match? Not going to match. 11, 12, 13 doesn't match against 1, 2, 3. Our second one, is this going to match? Not going to match because it's a tuple. It's not even the same data type, data structure. So 1, 2, 3, it's not going to match. Okay, is this one going to match? It's going to match 1, and then 2 is going to get bound to X, and then 3 is going to match, and we're going to be good there. Okay, this would also match, but it won't match because the one above it did match. If instead of 1, 2, 3 we had passed in 1, 2, 3, 4, 5, this one would match, and the one above it wouldn't have, and our 1 would have hit, and our tail would contain everything after our first element here. Okay, boink. It's just pure candy. I mean, it didn't have to have this, but it's just nice. This is handy. We can have these little digit separators. Inside the language, Erlang was really known for being terrible at strings, and Elixir is one of the best languages out there with strings. It's amazing to take the thing that was the worst in the previous language and then have it be the best. So that's very cool. Anonymous functions. So we use these a lot. And we also have this convention of we can put a question mark at the end of something if it's going to be a bool. So we have odd. We're going to define this anonymous function that takes an input, and we're going to take the remainder of whatever gets passed in, divide it by 2, and if it's not equal to 0, then we know it's an odd number. Now this function, say odd of 5, odd of 8. And there's a shorthand. We use anonymous functions so much there's a shorthand here where we say ampersand, and we have the same thing rather than having the fn and the end, we have ordinal positioned so that ampersand 1 is going to be our first argument that came in. Same exact thing, no difference between those two other than which fits your scenario. So, we also have an idea of multiple function heads. So in regular code, in Elixir, we can have multiple function heads for the same function. Here, inside of an anonymous function, we can as well. So we're going to define this anonymous function that has one head of square width, rectangle width height, circle radius. We fall through. We call area, pass it to square, rectangle, circle. Very cool, right? So in functional programming, we go inputs to outputs. We take data on the left, and new data comes out on the right. We're not mutating things. A goes to B. And that's such a common pattern that in Elixir we have this pipe forward operator that is going to take the thing on the left, and it's going to pipe it in as the first argument to the expression on the right. We'll see that used inside of a enum and stream. So here we have our same odd function. And we're going to have this range of numbers from 1 to 100,000 with our little digit separator. We're going to pipe that forward. And so if you're in the REPL and you need to have this in multiple lines, this is the way you do that. It knows that the line's not over by putting the pipe at the end, which looks a little funny, but it works. And so we pipe forward into a enum map. So our argument comes in as this implicit first argument here, and our function comes in as our second argument there. Our argument times 3. So we're going to triple whatever comes in. We're going to filter out by odd. We're going to sum these. We get a big number. We say the same thing with the stream map, stream filter, and then a enum sum. They do exactly the same thing there, as far as we can see. They both implement the enumerable protocol. So this is like an interface in other languages. But the implementation is different. So enum is going to do batch processing, where our data chunks through step at a time, all coming together. And stream is a lazy pull, and the data is going to get pulled through as a one-piece flow. Maps. This is our go-to structure in Elixir. We use these a lot. So we have Bryan beer defaults. And we can access a property or a key within a value by its key. And we can do this by an indexer saying atom name and get this. And there's a macro inside of Elixir that gives us candy on top of that. And if the keys are atoms, then we can refer to it as person.name. That's nice. We can build new maps based on an existing map that we have handy. So here we're going to create a new map based on the person, but we're going to have a different name. So a new map comes out of the right of it. And if we have we try to build a new map off of our existing map and we put some property that's not there, it barks. Keeps us from making a goofy mistake there. If we really need to do that, we'd create a new map based on the old one, and we would put a new key in it, and we get a new map that has awake in it. Okay? Structs are really powerful. There's a little bit more involved in it. We've created this module called person, and inside of it we have our def struct. So we have this structure that's going to have defaults, and let's see how it behaves. So if we say person, so this is something that we could know about, pass around the world. We can define contracts between different parts of code here. So we know the things that are there. It's not just whatever we thought of when we need one of these up. Bryan. And we say person, name, Bryan, bar defaults, boom. Because that wasn't defined in our struct. So we get a compile time error there, which is really good. It's quite unlike what we'd have if we were in JSON. Okay. Let's see. We're very close to time, aren't we? Are we 2 minutes away? Is that right? Okay. Okay, I'm going to make a hop here. What I have, one of the things I want to show is I have a repo. Wait, no, we have 3 minutes, something like that. So let me hit this real quick. So we're going to talk about macros for just a second. So we have fridge check. So we get our fridge, it returns an OK, and then a list of temperatures. We say a new max. We're going to get the max. Oh, wait, what? OK, so our thing came back with an OK and a list of things, which we can't pipe into a enum here. So that sort of stinks. So we would do the grown-up thing and say OK, temps, and then catch the result of it, and then take temps and pipe into a new max and we get our value. Or we could do the crazy wild thing, if this was a pain point in your company, and you could define a macro. Anything that you don't like, you can always define a macro. So here we're going to define this macro called bang pipe. It's going to have a left-right pipe. It's goofy, but so we're going to import this thing. I'm going to show you how this works. So our fridge check is the thing on the left, and our new max is the thing on the right. So what happens in our macro, when it sees this, it's going to replace the thing on the right, basically like build this string up is a way of looking at it, and it's going to put fridge check in there. It's going to pipe fridge check into our case statement. If it's okay value, we're going to get our value. If it's not okay value, we're just going to return whatever we had, and it's going to then take that and pipe into whatever was on the right side of our operator. And so we get this, and that's, this is really a dumb example, but I just wanted to show off the idea of macros. And also wanted to give this sort of warning about when you should write macros. So you write macros when you're Jose, or if Jose personally asks you to fly his sleigh tonight and write a macro. And you could also, if your team has decided the pain of not having the macro is more than the pain of having that macro. Because as new people come in, it's going to be hard to understand what's there, and it's going to slow your team down. It really comes down to the cost of it. All right, and so we're going to not talk about the bit syntax. What I'll do is on the things that we couldn't hit here, I'm going to skip on by, and those will be up on the GitHub repo. And so hopefully that was a Bellyful. I'm not quite sure. So don't know that metric exactly. But so we have that Bellyful, and the close I'd like to say is, we have this amazing platform. It's stunning. There's nothing out there in the world like it. You can't build this stuff up on the JVM. Can't build it up on the CLR. No company is going to come and write the Erlang VM again. It was a special time when that thing was built, and there's nothing like it, and Google's not going to build it, Microsoft's not going to build it. It's there, and it's the only one out there like this. It gives these superpowers. So we have those guys on the left to thank for that. And this guy on the right, we have to thank for having the wisdom to see what was there. And also having the compassion to bring us all along with him. And so it's just this amazing thing, very thankful for this crew. And I guess all we have to do is just take this good stuff and go have fun at work. And that's where we're at. And that's the Bellyful that we had. So hopefully you all are having fun with Elixir. We're really out of time, so we don't have time to do the questions. Here, this GitHub repo will have the stuff in it later. And follow, hit me on Twitter if you have any questions about anything. But thank you all for being here.